Thanks for joining us about my favorite topic, soils. So Andy, if you want to go to the next slide, please. Okay, just there's some objectives of part 1 of module 1. Hopefully after this training, you'll be able to understand and explain the definition of soil, understand and explain what a soil description is, and understand and explain the difference between soil properties and interpretations. Next slide. So why the heck should we even care about soil? Well, this slide here, I think, kind of says it all, right? Soil is vital to life. We cannot live without it. It's not a renewable resource, and if it's unprotected, soil is very vulnerable to wind and water erosion. So the photos here on the left are taken from something you might have heard about called the Dust Bowl in the 1930s, and it resulted from drought periods, high winds, and improper stewardship of the land. This was very devastating. People lost their lives, livestock, and the economic devastation lasted, the dust storm lasted about a decade, and the economic devastation lasted even longer. So look over here on the right-hand side of your screen, and it doesn't look a whole lot different on that top right, and that's a picture in Iowa. Recently. So we're still faced with these resource concerns of water and wind erosion. So bottom right here, we've got water erosion. So where does that water go? Goes into our streams and our ditches, and it's not very clean. So we have water quality and air quality issues. Next slide, please. So here's a definition of soil. You guys can read that, but I agree with Hans Jenny, and the soil is my friend. And to the left there is our state soil antigo. So every state has a state soil. Again, soil is vital to life. Next slide, please. So what exactly is soil? Well, if we look at this graphic in the middle here, we have this pie chart, and we have 50% that is solids and 50% that is pore space. The composition is pretty simple, but how those components are distributed and the total content and the proportions can drastically change how a soil reacts and responds. So on that left-hand side, we have the solids, and that is 45% of minerals, which includes our sand, silt, and clay, and 5%, which is organic matter. And this is the living or once living component. It gives the soil that dark, beautiful color. And even though it contains only about 5%, organic matter actually controls about 90% of the soil function. Then on the right-hand side here, we have the pore space, which is occupied by air and water, and this fluctuates, of course. Healthy soils act like a sponge, and the pore space, if you look at the top right photo here, that's a CT scan of a soil profile. And so that kind of looks like our own circulatory system. This is where the air, water, and nutrient exchange happens for plants. But if this pore space is destroyed, then these critical pore spaces are unable to function properly and efficiently. Next slide, please. All right, does anyone know any of the 5 soil forming factors? If so, feel free to start typing them into our chat. Hans Jenny is a Swiss soil scientist who came up with the soil forming factors. I don't see anybody in chat yet. All right, parent material, yes, that's one of them. Climate, very good, Josh. Time, Eric, very good. Yes, yes, yes. So we have 5 soil forming factors, and Hans Jenny came up with a mathematical equation to express this. So soil properties are a function of climate, organisms, relief, parent material, and time. And he left this open because maybe there's other variables that we're yet to discover that impact soil formation. Next slide, please. Temperature and precipitation influence the physical and chemical properties of weathering. Precipitation, the water dissolves soluble materials, transfers them either upward or downward in the soil. And water is needed to transfer clay particles lower in the soil profile. Temperature affects the rate at which chemical and physical weathering happen. When it's freezing, we pretty much stop pedogenesis or soil formation, just kind of like we all kind of stop too. But in Wisconsin, we do have the freeze-thaw process, which is essential in soil development and weathering of soil particles. And then, of course, chemical reactions occur at more rapidly rates during the summer when we have those hot temperatures and humid climate going on. But even if we look at these, so on the left-hand side here, that is the temperature, the average temperature over the past 30 years in Wisconsin, and then the one on the right or in the middle is precipitation. So even within the state of Wisconsin, we have different weathering processes because we have colder climates to the north and where the precipitation is. So we have different weathering rates even here in Wisconsin. Now this picture there over to the right is our Wisconsin tension zone, and that gray line there, that it kind of follows, and we'll talk about this a little bit more, our mesic frigid soil temperature regime. So of course north is going to be cold, frigid, and then the mesic is south of that line. Next slide, please. All forms of life, both in and on the soil, influence the chemical and biological processes of soil formation. So again, if we talk about that tension zone, and you can see in the map in the middle here, we see a bunch of green, and then we see like a yellow zone, and then there's that kind of wavy line. Again, that's kind of our tension zone. And so early vegetation here to the north in that green zone is our broadleaf forest containing those conifers, pines, spruces, firs, those needly things. And then in this yellowish area here to the south of that line, we have an oak savanna and tall grass prairie. So because of that vegetation in our early vegetation, different soils formed in those different regions. And we'll talk a little bit more about it. Don't get hung up too much on these names and things. But to the north, those needly things, that's where spodosols are typically found. And that's the picture there on your left. And they have different characteristics than what you see on the right there, which is a mollisol, which is formed from tallgrass prairie vegetation. And then also to the south there is where an alphasol, so those hardwood forests. So looking at the soils, if you're a soil scientist, I can look at that. I can tell you already where, what type of vegetation it was formed. Humans also impact soil development. We've cleared the native vegetation for farming, logging, and other purposes. We've accelerated the rate of erosion. We've impacted soil structure, pore space, and organic matter. We've applied fertilizer, changing the chemical and biological properties of the soil. And then, of course, we have artificial drainage, which impacts the natural drainage of the soil and the chemical properties. Next slide. All right, elevation, slope percent, slope aspect, slope shape, and the landscape position all impact pedogenesis, the soil formation. Many conservation practices are designed to reduce the slope gradient or percent to minimize soil erosion and increase infiltration rates. So as planners, you really deal with slope percent quite a bit. And then it's also good to know what landscape position you're on, and that's on your bottom left here. That influences the natural drainage. And also you want to know what type of, where you are on the landscape to know, do you have erosion happening? Is this a place that's naturally susceptible to erosion or deposition? So that shoulder part is convex and it's subject to erosion. Whereas when you get towards the foot slope position, that's more of a concave location and you'll have more of a deposition. Next slide, please. All right, this is where it gets really cool, guys. All or part of northern and eastern Wisconsin was covered by ice during the last glaciation. There were several different advances. several different lobes, but there was a big portion of Wisconsin that was not covered by the glacier, and that is in the western portion, and that's called the driftless area because it lacks the glacial deposits. The glacier left Wisconsin approximately 10,000 years before present, and that's what formed our landscapes. So that's why in the north we have a lot of lakes, the central portion is pretty flat, and then the eastern portion we have some rolling hills. So with the glacier, we have several different variations of parent material. And again, if you look at the picture in the middle there, again, you kind of see that same little squiggly line there with that tension zone. And in the yellow, that portion is the driftless area, so that was not covered by the glacier. And then the other portions was covered by the last glacier. We have several different parent materials that our soils have formed in, including, and we won't go into detail, just we'll mention them. These include till, outwash, lacustrine, loess, alluvium, and organic materials. And these different parent materials have different properties and they react differently to management. Then this picture to the right is our bedrock geology. And again, we have several different bedrock that exists in Wisconsin, like gneiss, granite, slate, quartz, sandstone, shale, and again, different characteristics, and they behave differently being weathered and throughout the pedogenic process. So remember, soil is it's weathered rock. Next slide. The length of time the parent material has been exposed to the soil forming processes influences the nature of the soil. So we have 12 different soil orders, 7 of which actually exist in Wisconsin. And man, if this just doesn't excite you here, I don't know. Come on, guys. I wish I could see all your excited faces. Soils have been forming since the earth has been turning. It takes a long time for soils to form. And in Wisconsin, that driftless area, those are our oldest soils. Whereas in glacial time, the soils that formed in the last glaciation are very young soils. So they've only been developing for the past 10,000 years. The soil forming factors are not constant. They change over time. And if there's one thing that I know, it's that soils are variable. Okay, next slide. So we have to have an understanding about what soil is and how it's formed to then be able to describe the soils. Field soil scientists describe the physical properties such as texture, structure, and color. And these properties can help us infer the chemical properties. We can measure some or estimate some of the chemical and biological properties in the field, but certain things we definitely have to send to a certified lab. Next slide, please. All right, let's talk about the USDA soil texture. These are the particles that, and they're categorized into groups by size. We have sand, silt, and clay. Sand is our largest and clay is the smallest particle size. So anything less than 2 millimeters is considered soil. If it's larger than that, then we call it a coarse frag, so gravel, rocks. But if it's bigger than that for USDA, it is not soil. Soil texture is the numerical proportion, percent by weight, of those particles, sand, silt, and clay. And we can add those up to 100. You'll see here that soil scientists, we like to keep things pretty simple. In the middle here, we have a USDA textural triangle, and that has our 12 classes of our textural groups, and they're based on behavior. And we can estimate the soil texture in the field by feeling it. So typically we will estimate clay because we can try to make a ribbon. So that's what's showing here on the top right. And then we can feel sand, it feels gritty. So we can put a sample in our hand, pond it with water, and then feel that grittiness. And then if we can estimate the percentage of those sand and clay, and then if we need to, we can then calculate the percent silt. This can also be done in the lab, and of course it's much more accurate to do that. One thing to note on the textural triangle, and Andy, can you show, when we read percent sand, it actually goes on an angle, Well, we kind of angle it there, and then percent clay goes straight across. And then the percent silt comes again on an angle. And one thing to know here is that the left-hand word is actually a modifier, and the right-hand word is like the dominant behavior. So if you look at the bottom left-hand side, we have a sandy loam and a loamy sand. Now this could be tricky. It might be on a homework question. I don't know. So which one of those would actually contain more sand? A sandy loam or a loamy sand? Somebody type it up in chat for me. What do you think? More sand in a loamy sand or a sandy loam? I don't see any chat going on. A loamy sand, right, because that right-hand word, not even just looking at the triangle, so if it was on a written test and you didn't have the triangle in front of you, that right-hand word is actually the dominant factor. Good job, good job. Knowing the soil texture can help us understand some of the limitations and how to manage the soil. All right, so we see on here we've got clay, we've got loam, silt loam. Next slide, please. Well, shoot, I know some of you are probably like, well, Jen, we've heard about these things called organic soils. That's not on your triangle. And you're right. So they're kind of all on their own. Organic soils have developed in saturated and anaerobic conditions. I highly recommend taking a Hydric soils class. It's phenomenal. I love Hydric soils. I love organic soils. Anywho, so an organic soil versus a mineral soil, the organic soil contains 20% or more organic carbon. And we have muck, which is highly decomposed organic material. We have peat, which you can still see the fibers in there. And then we have something really geniusly called mucky peat, which is in between those. And so for the textures, for muck, it's sapric. Mucky peat, we have hemic or hemic, and then we have peat, fibric or fibric. All right, next slide, please. Then we can talk about soil structure, another thing that we describe in the field. And this is the arrangement of particles into aggregates, or we can be fancy and call them PEDs. And the soil structure is really important for how water and gases move in, out, and through the soil. So just really basically here, we have granular structure, which shockingly looks like granulars or cottage cheese. Again, we like to keep it simple. Blocky, whoa, it looks like blocks. That's typically found in the B horizon. I should mention the granulars typically found in the A horizon. And then we have platey structure, which is horizontal plates. And this is typically in the E horizon, but it can also be in horizons that if we have some compaction going on. We have prismatic structure, shocker, looks like prisms. Again, typically found in the B horizon. Then these last two, we have massive or single grained. And if you look at those compared to the other structures, it is what it is, right? It's massive. There is really no structure there. Or single grained, it's just a pile of sand. So there's no distinct structure. And these are typically found in C horizons or that massive structure. Unfortunately, if it's disturbed or has been tilled for several years, we can have that instead of that beautiful cottage cheese structure, we can have that in our A horizons as well. Okay, next slide. My favorite, and I hope this excites all of you, is soil color. Look at that, it's amazing. The first time I ever took a soils class and saw this, I was like, holy heck, who knew that soils could have different color other than brown or black? Like you dig a hole in your backyard, it's black, right? Well, I guess if you're in Munsell country. And there's all these different colors and these colors mean things like mind-blowing, mind-blowing. Our uncoated soil particles are actually gray or white in color. And we have two dominant pigmenting agents that kind of paint those soil particles. So those dark colors up at the top there, sorry, I can't use my cursor. So Andy, if you want to show where the dark is, that's due to organic matter, which gives the black or brown color. Then our second pigmenting agent is iron, which gives that red, orange, or yellow color. And it's a very important property. Soil scientists can infer how the soil was formed, which native vegetation it was formed under, the history of the soil, was there some sort of a disturbance or erosion happening, where the seasonal high water table is, we can infer chemical properties and potential uses of the soil. All right, so how do we color the soil? How do we note that? Next slide. So we can say things are brown or yellow or whatever, but your eyes see things a little bit differently than my eyes. So that we're communicating the soil color and we're all on the same page, dun-dun-dun. We use the Munsell color charts. And there's three aspects that we describe. It's the hue, the value, and the chroma. So in the Munsell color book, on now the new ones have tabs, which are very helpful, and that gives the hue. And then there's also a part in the upper part of the chart that will give the hue. And that's the dominant spectral color. Then on the left-hand side of the book, sorry guys, I don't have a mouse, so that's the value. And that is the lightness or the darkness of the spectral color. And then on the bottom, on the horizontal portion, is the chroma, and that's the purity of the spectral color. So we have to give three components when we describe the soil: the hue, the value, and the chroma. So for instance, if where that arrow is pointing, and I think that my color matches that bottom left-hand chip, I would call that 10YR. That YR does not stand for year. It actually stands for yellow-red. So I'm on the 10YR page. And then my value is 2 and my chroma is 1. Then there's a cheat sheet on the other side if you're curious, which we don't really ever use that. We talk about the hue, value, chroma. But on the left-hand side, there's a cheat sheet and it tells you what is that color. So 10YR21 is black. And again, it's just a way for us to be able to communicate soil. If Andy said to me, hey, I saw this really cool soil, the major color of it was 2.5Y52. Boom, I've got it in my head. It's a beautiful gray. It's a wet soil. Boom, done. All right, I love soil color. All right, let's move on. Next slide. So once we have described our soil texture, our structure, and our color, then we can start to designate these master horizons. And we're just going to talk about the master horizons, not the subscripts. There's more detail. And then this picture in the middle is idealized. I don't think you're ever going to find every single one of these horizons when you dig a pit. So let's start at the top. Oh, and I should say that these are these layers or horizons. They have unique chemical, physical, and biological properties. So that's why we know what they are and how to assign them. So at the top there we have an O horizon, and that's fresh and decaying plant residue and other organic matter accumulations. Then we have the A horizon, and this is mineral. And it has a high proportion of organic matter. That's why it's that dark color. Remember, organic matter is one of our pigmenting agents. And then we have E horizon, which is light colored. It has the maximum zone of leaching, eluviation, don't worry about it. And there's typically depleted areas of clay but not very much organic matter here, and it's white and grayish in color. I know if I see an E horizon, I'm in a forested, it was native vegetation was in a forested area. Then we have a B horizon, and this is the maximum zone of accumulation. So we can have an accumulation, depending on where you are in the world, of clay, iron, aluminum, carbonates, gypsum, and then this is a zone of illuviation. We won't get into all that, but I have to throw that out there. Then below that, we have the C horizon, and this is relatively unaltered, unconsolidated parent material. So we still dig into it. It still looks like soil, but there's just not a lot of stuff. It's not real different from the parent material, not a lot going on. And then we have R, which is bedrock, and of course we would find that quite a bit in our driftless area. Okay, next slide. So once we describe the soils, and then we can classify the soils, And we can map these soils. Well, they're kind of grouped on their soil property. So let's talk about what a property versus an interpretation is, because when you're doing your planning, you're probably looking at soil properties and interpretations. So a property can be measured or inferred directly in the field or with lab. It's the characteristics and qualities of the soil, and it has impact on land use and ecological purposes. The properties are used to classify and map soils, and it's the foundation. These properties are the foundation for the interpretation. So you have to understand the properties so then we can develop interpretations. And Kristin will talk more about these properties, and then we have those interpretations. And basically this is predictions about how the soil will behave, and they're typically assigned suitabilities and limitations. Andy will dive into this. Again, they're based on those soil properties, and they could either be an entire map unit or a map unit component, which Jeremy will talk about later. So really, we have to have an understanding of what soil is, how it formed, to be able to describe it, classify it, map it, develop our interps that are based on the soil properties. Now, Kristin will go more into detail about those soil properties. Kristin, it's all yours. Take it away.
Good morning. Hello, everyone. I am Kristin Foehringer. I'm a soil scientist out of the Altoona area office. I started about 3 weeks ago, so I'm new to this position, but not necessarily new to soils. I get the privilege of diving into soil properties, so we're going to cover 2 categories, inherent and dynamic. I'd like this to be as interactive as possible, so if there are any questions, if I say anything incorrectly, if you need clarification, type it into the chat box. There's a bunch of folks on here who can provide some more detail. And also think about, as we go through these properties, which conservation practices can be impacted by properties, or how it determines your decision-making processes on a day-to-day basis as a resource professional, planner, technician. As Jennifer mentioned, you know, soils are really the foundation to a lot of the decisions we make from a resource standpoint. So, all right, so what are soil properties? So they're attributes of soil that can be measured or inferred from direct observations in the field or lab, as Jennifer mentioned. They're characteristics and qualities of soil that have an impact on land use and ecological processes. They're used in a myriad of different ways. So we use them to classify and map soil. We use them to predict soil behavior. They're the foundation for soil interpretations. We use them to predict expected responses or behavior of soil under different land uses or management regimes. And we use them to determine suitability or usefulness of different conservation practices. Typically, we lump soil properties into different categories. These include chemical, physical, biological, soil health, water features, and erosion factors. I think it's important to note that these properties aren't necessarily black and white or a one-size-fits-all. So you'll probably see that as we go through some of these. So the 2 categories that we're going to focus on are inherent and dynamic. So inherent essentially changes very little, if at all, with changes in land use and management. So this is reflected in land capability classifications. If you look at that figure on the top right, you have soil quality on the left, or the y-axis, and then time on the x. You see that given 2 different soil types, the properties change very little over time, so basically on a human time scale. And then if you look at dynamic properties, these are properties that change with land use, management, disturbance at the human time scale. So we can see these, you know, on a decadal or some, you know, within our lifetime. So you can see you can aggrade or degrade soil quality, and then soil quality is basically a combination of inherent and dynamic properties. I saw in the chat someone was asking what would classify as inherent or dynamic. Please use the chat, and why don't you throw in there some what you consider an inherent property versus a dynamic property. And we'll move along, and I will give you the answer on the next slide, please. Andy, can you change the slide? There we go. All right, so dynamic properties include attributes like organic matter, soil structure, infiltration rate, bulk density, water holding capacity, nutrient holding capacity. So changes in dynamic properties depend on land management practices and the inherent properties of the soil. Examples of inherent properties, so these are things that are based on those soil forming factors, so things like soil texture, depth to bedrock, the type of clay and the mineralogy of the soil, the cation exchange capacity, drainage class, things of that nature. So again, you know, in soil science, you have your lumpers and your splitters, I'm sure you've heard. So this isn't necessarily a black and white situation. So for example, organic matter levels in the soil depend on tillage practices, the types of plants growing or the management, but the total amount of organic matter is constrained by things like soil texture and climate, so those inherent features. And then you look at a property like bulk density, which is typically considered inherent or could be considered inherent if you're looking at the subsurface horizon, so like 20 to 50 centimeters, sorry, I'm using metric units, but are more dynamic at the surface where you might have tillage influences on, you know, properties like bulk density. Next slide, please. So this diagram kind of shows how dynamic soil properties on the right support or influence soil functions. So the functions are what we want our soils to do or to provide for us. So if you look at things like stability and support, water relations or dynamics, nutrient cycling, filtering and buffering of pollutants, biodiversity and habitat, all of those functions are influenced by dynamic soil properties. Dynamic soil properties are influenced by management and the inherent soil properties. Next slide, please. All right, so Jennifer touched on soil texture, so I'm not going to go into a lot of detail on this, but soil texture is considered an inherent soil property. So these are the relative proportions of sand, silt, and clay. So the fine earth fraction or the mineral fraction. As Jennifer mentioned, this is excluding organic material or organic matter. And you know, it's really important to think, it influences physical and chemical properties of the soil, and those can influence things like crop growth. So soil structure, organic matter, aeration, bulk density, water movement and storage, weathering of minerals, nutrient supply, etc., are all influenced directly or indirectly by soil texture. So if you think about the impact on crop growth, if you have a clay soil versus a sandy soil, the water holding capacity of those are different. So clay could be excessively wet, whereas sand could be droughty. So it's important to consider texture when you're doing conservation planning. Next slide, please. So this figure demonstrates the differences among textural systems and particle size scales. So it's important to note that I think agronomically we typically focus on the USDA system versus on the engineering side of things we use the unified system. So the major difference is that the USDA system considers grain size and mineral fraction, whereas the unified systems consider clay mineralogy and how it affects water holding capacity, plasticity characteristics, which we'll talk about. And those things aren't evaluated with the USDA system. So they're very much different languages that are talking about similar things. But if you take a soil mechanics class, you'll see some of the major differences, and the focus for engineering is much different than what we look at agronomically. Next slide, please. So this slide demonstrates the unified system. On that previous figure you saw, there was a break in the different cutoff points or grouping categories among USDA unified, and then the AASHTO system, which is typically used for roads and things like that. In NRCS, we typically use unified and USDA. So in the unified system, we have these major divisions of coarse grain soils versus the fine grain soil fractions, and then their group symbols are much different. So for example, if we're talking about a silt loam, that will probably be categorized as an ML under that group symbol. So those are typically our silt loams. The group symbol determines workability. It determines if you can use certain soils for engineered practices. So if you think about manure storage systems, or if you're trying to build an embankment for a dam, your soil properties determine whether or not you're going to have seepage, if you're going to be leaching chemicals. So it's important to understand and recognize that these are different. And at least it's actually This book has a great example, the field book for describing and sampling soils, and it goes through each system in more detail. So that's one place you can start if you're curious to learn more or take a soil mechanics class. Next slide, please. So this table does a really great job at talking about how sand, silt, and clay separates are influenced or influence different properties and behavior. So this is as an example, if you're talking about water holding capacity, like we talked before, sand has a really low water holding capacity, clay has a pretty high water holding capacity. So this shows how each of those particle size influences different behaviors in the soil. Next slide, please. All right, so these topics admittedly are pretty complicated, so we're just going to touch on them. But as far as inherent soil properties, the soil mineralogy, the clay content, and plasticity are really important in how they influence soil behavior. And one thing I want to point out in this figure to the top right, we're looking at different types of minerals. So minerals are naturally occurring inorganic compounds that have a characteristic chemical composition. So if you look at quartz, for example, you can see that it essentially contains no plant nutrients. So the inherent mineralogy of your soil can determine it's what I would determine as like an inherent fertility. So for quartz, if you know that's part of your mineralogy, you're not going to have a bunch of nutrients in there. But if you look at things like feldspars that contain potassium, calcium, magnesium, copper, or some of these other minerals, that can determine your fertility of your soil. Knowing the structure and property of the soil minerals is really essential for understanding some of the mineral transformations. So weathering, transport of nutrients, everything that kind of influences soil genesis, the development of those horizons, structure. So it's important to have a pretty good understanding of what your soil is made up of. Getting into clay content, as we briefly touched on, clays have a much higher water holding capacity and nutrient holding capacity than sands, for example, and they're typically classified as a 1-to-1 or a 2-to-1 clay. So you'll hear about shrink swell capacity, things like that, but that's really just the different types of sheets and layers that these clays have. So in Wisconsin, for example, we have some 2-to-1 clays like a montmorillonite, which can have water go in between those layers and you might get some shrink and swell, versus a kaolinite, which is a 1-to-1 clay, which you would want to use if you're trying to seal off a surface. You don't want water to get in there. So it's important to think about your mineralogy and the types of clays that you have in your soil when you're designing a structure or implementing conservation practices. All right, next slide. And engineering plasticity is really important, so I just want to briefly touch on it. So essentially, it's the soil's ability to undergo deformation without cracking or fracturing. So it's kind of its workability. It's directly influenced by the mineralogy, the clay content, the particle size, and the water content of the soil. It's typically determined in a lab using Atterberg limit tests. There are some field techniques to determine some of the engineered soil properties. But again, if you need to know for like a manure storage or a chicken barn or something like that, you would want to get a lab test to determine plasticity. But essentially, if you look at this figure, it's the difference between the liquid limit and the plasticity. So the plastic limit and the liquid limit. So that's your plasticity index that we use and you'll hear referred to on the engineering side of things. So I guess this is more of a place you can come back to if you need more information, but just acknowledge that plasticity is a really important characteristic of soils, especially on the engineering side. And like I said, directly influenced by mineralogy and clay content. Next slide, please. Kind of beating a dead horse at this point, but anyway, so when we do those lab tests to determine plasticity indices, as you can see, the index is on this left axis and then the liquid limit is on the right. Most soils fall in between those two lines called the A line and the U line. If it's below that A line, it's a non-plastic soil. So again, those are the unified classifications. You see CLCH within there, demonstrating differences in the liquid limit and the plasticity index. And then anything under that would be considered non-plastic soil. So difference in clay content mineralogy, and then nothing is plotted over that U line. So if you see something like this, that's what it's trying to demonstrate. Next slide, please. All right, so another inherent soil property is cation exchange capacity. So this really, if you hear about CEC or cation exchange capacity in a soil, it's basically a measurement of the nutrients available for plant uptake. So there's many ways to measure it. We typically work with effective CEC, so nutrients available for the plant to take up. Soils vary in their CEC. That figure to the bottom, or that table to the bottom right, kind of shows you that sands have a pretty low CEC, whereas clay and organic soils have a much higher CEC because they have these they have charged surfaces that can hold those cations. So positively charged ions are called cations. You can see in that figure a soil with a low CEC only has a few holding places, whereas high CEC can hold many more. Roots kind of produce their own environment where they can knock off cations on soil particles and then absorb them for plant uptake. So that's something to consider. This plays a big role in fertility of soils. So if you have a low CEC soil, you can have nutrient deficiencies, leaching losses. pH can change easily with soil amendments or irrigation. You might need more fertilizer in these environments. High CE soils, they have a greater, we call it like a buffering capacity. They can resist change to pH, greater retention of nutrients, reduced leaching losses, generally higher fertility, higher productivity. Next slide, please. Another inherent property that we deal with frequently are restrictive features. So we encounter in Wisconsin features like a depth to bedrock. So a shallow rooting depth can have infiltration issues, depth to water table, perched water tables, glacial till in some parts of the state. I'm over on the driftless side, so we don't have a lot of issues with glacial till or any glacial features because the glaciers didn't get here, but we do see depth to bedrock issues and redox features associated with high water table levels. So on the figure on the left, you can see a very shallow depth to bedrock. So this influences how water moves through the soil, rooting dynamics, what kind of crops or vegetation can grow on a soil. It affects engineered practices. So if you have a shallow depth to bedrock, you may not be able to install a practice, or it could significantly increase the cost of installing if you have to start, getting the rock out of there to install something. The second figure shows some redox features. So you have depletions, iron accumulations. On the top, you can see a little black spot. That's a manganese concentration. So when you're talking about hydric soil indicators, these are formed, which is what this is demonstrating. They're formed by the accumulation or loss of iron, manganese, sulfur, carbon under saturated and anaerobic conditions. So if you have water, a high water table, you have a depletion of oxygen, you have roots can't really survive down there without oxygen. It changes your microbial community. So these are things to consider from a conservation planning perspective and from an engineering perspective. If you have fluctuating water tables, that could impact a practice. And then the figure on the right is kind of showing the variability in depth to water table across the state. So it's definitely different depending on where you go. And these can affect different conservation practices. Obviously, if you're trying to install a fence and you have a shallow depth to bedrock, you might have some challenges. So something to consider. Next slide, please. All right, so moving on to dynamic soil properties. So again, these are things that we can change with management or land use, and they're not static. So these, the first one that we're going to talk about is my favorite, which is soil organic matter and soil organic carbon. As Jennifer mentioned, organic matter really drives most of the functions in soil, and while it's considered a physical property in most cases, it's really sort of in the middle of these physical, chemical, and biological soil properties. And if you're going to alter anything in soil, I feel like increasing soil organic matter will get you the most bang for your buck as far as effort goes. So again, it's crucial for most soil functions and ecosystem services, things like nutrient provisioning, water holding capacity, soil drainage, soil stability, aggregate stability, greenhouse gas emissions. It influences and mediates most of those processes. So soil organic carbon can be a sum of organic carbon, elemental carbon, and inorganic. The inorganic and elemental components are pretty insignificant in most soils. Definitely in Wisconsin, we're talking mostly about organic carbon. So it's that organic fraction of carbon in soil. And organic matter is the decomposed plant, animal, and microbial residues. It's usually expressed as a percentage by weight in the fine earth fraction of soil. So back to that textural triangle, anything less than that fits in that triangle. And then it's different than total organic carbon in that it includes hydrogen, oxygen, nitrogen, other elements. And it's about 58% carbon. So if you know your organic matter content of the soil, you can calculate and convert it to total or soil organic carbon. And I really like this cartoon because it kind of demonstrates the really complicated process of decomposition and how organic material from the above ground can be incorporated into the below ground component. So I thought that was a cute demonstration. Next slide, please. All right, so how do you know if your soil has a lot of organic matter in it? Jennifer talked about color quite a bit. So color is a pretty good indicator. If you have darker brown soil, you think about topsoil, or a healthy soil is going to have that dark brown color. That's organic matter. You look at that figure to the picture to the bottom left, and you can see a comparison in different grazing systems. The one on the left has much higher organic matter or carbon content than the one on the right. And then my point with the figure on the right is that all soil organic matter is not created equal. So the categories of soil organic matter, from how quickly it decomposes, changes probably as much as the seasons and how people define it. But I would put it into two camps, where you have your fast cycling soil organic matter and your slow cycling matter. So I like the analogy that it's very much like a checking account versus a savings account. Essentially, your checking account is what's fluctuating regularly, daily, weekly, monthly, and you're putting inputs into that checking account more frequently than you would your savings account. Your savings account, you know, if you're doing a home renovation, you're going to pull money from your savings. Same as if you're going to convert a prairie to a farm field, or, you know, a cultivated crop, or a forest to an agricultural field. You're going to lose a lot more of that carbon in that kind of a land use change versus like if you're tilling. So just recognizing that there are different pools of organic matter, and the one that you want to invest in is this mineral associated organic matter, because that's slow cycling and more resistant to change. So when we talk about soil carbon sequestration, understanding that there's different pools, and that if you want that longer lifetime of carbon, you want to put it in that slow cycling pool. And so there's a difference in pathways on how carbon gets into the soil and organic matter, but that could be a month-long discussion. So next slide, please. This is a busy slide, and that's on purpose. So this schematic demonstrates the importance of organic matter in soil processes and ecosystem services. Basically, by manipulating soil organic matter, it has this chain reaction effect on many, many other services and functions in the soil. If you're trying to increase plant productivity, yield, health, any of that, manipulating the residues in the soil, residue management, reduced tillage. I mean, all the principles of soil health are kind of centered on this idea that organic matter really drives a lot of the processes and functions in soil. So that's what this is demonstrating. Next slide, please. All right, soil structure is another dynamic soil property. If we're talking about the surface horizon, sometimes those subsoils don't change as much or within our lifetime. Really depends on management and land use. But Jennifer went over this, so I don't need to talk about it in great detail. But essentially, it's the arrangement of particles into aggregates, which are called PEDs. And we break them down into that granular cottage cheese structure, the prism, the blocky, etc. So structure really boils down to how fast water can flow through the soil, how easily plant roots can penetrate the soil, the aeration of the soil, roots need oxygen. The stronger the structure, the faster water and roots can penetrate. So granular being essentially the strongest structure. So that's what we're working for, and management affects it. So that's something that you can work with producers. Show them that platy structure if they have a lot of tillage, and then, you know, contrastly look at a healthy soil that would have that granular cottage cheese structure. Next slide, please. So when we talk about structure, I think the main focus is really these aggregates. So aggregates form when soil particles stick together. You know, they're cemented or glued together by clay, organic matter, microbial exudate. So as microbes, bacteria, and fungi break down, as they excrete different compounds, that's really the glue of the soil that helps build these aggregates. They can be cemented by iron and aluminum oxide, silica, lime, root hairs. So the more diversity you have in your soil, the better off your soil structure, essentially, because you can build those soil aggregates, which are really important for resiliency in a system, resistance to drought, nutrient availability, and essentially poor management destroys this structure. So it's really important to, you know, that's why we, again, the soil health principles, keeping live roots in the soil, keeping your soil covered, all of this can help build your aggregates. Next slide, please. All right, so bulk density. We typically talk about bulk density as a measure of soil compaction. So this can both be inherent and dynamic, more dynamic on the surface of the soil, you know, those upper horizons versus the lower horizons. But it's dependent on soil texture, so an inherent property, the density of the soil minerals. So sand, silt, and clay, and organic matter. Basically, the more compacted your soil, the higher the bulk density, the heavier the soil is, because you're compressing that 50% that should be basically pore space. A high bulk density restricts rooting depth, water infiltration. It can influence the uptake of water and nutrients by the plant. The calculation for determining bulk density is on the right, but basically a rule of thumb is rocks have a density of 2.65, essentially. If you divide that by 2, assuming half of its pore space, an average soil, a medium textured soil with half pore space has a bulk density of 1.3. So if you go to the next slide, I can show you a spectrum of bulk densities based on soil type and management regime. So again, a lot of agricultural soils kind of fall at that 1.3 in the middle. And you can see the difference between a cultivated soil and an uncultivated soil. Soils like histosols or andisols, they have a much lower bulk density because of those soil forming factors, their mineralogy. But the biggest take home is that management can impact soil bulk density, and then that has a whole chain reaction of how it influences water and nutrient dynamics. Next slide. Well, oh, one other point. Actually, yeah, next slide's fine. Engineers like to compact the crap out of their soil, right? So from an agricultural perspective, we think lower bulk density is typically better, but if you're trying to design an embankment for a structure, you have to have the right soil material and compaction so that you don't have water moving through. So it's important just to look at both of those perspectives, and then understanding, you know, this image is showing that bulk density changes by horizon, can change by horizon and with depth. Traffic from agricultural vehicles and plowing, things like that can create plow pans, restrictive layers. So knowing that, you know, depending on where you're taking a bulk density sample, you're going to have different bulk densities throughout a soil profile, and then that influences rooting dynamics and water dynamics. So not looking just at the surface, but trying to think about the whole soil profile. Next slide, please. All right, soil pH or soil reaction. So we typically refer to soil pH as a measure of the acidity or alkalinity of a soil. So whether it's acid or base, as you can see on this spectrum to the right, it's typically on a scale of 1 to 14, 1 being most acid and 14 being most alkaline. Soils normally fall in the range of 3 to 8. Forested soils, things with high conifer component, are on the lower side. You know, a pH of 4 is not abnormal, whereas most agricultural systems are on the more neutral side, so kind of in the middle, because that impacts nutrient availability, crop growth, and management can definitely impact soil pH. If you go to the next slide, you can see that this is something easily measured in the field and one of the easiest things to manipulate. So in the field, you can do a 1-to-1 mixture of water and soil and use these little strips to determine your soil pH. Again, that's at the surface, but one of the most impactful management tools if you have a low pH and you're trying to raise it is liming. So it's super economical. It can, raise your soil pH to that more neutral levels so that you can improve yields and crop growth. And pH is something you can typically see in the leaf. If you have nutrient availability issues, it's likely related to soil pH in a lot of ag systems. It's influenced by the soil type and some of the other mineralogy, but again, management can greatly influence soil pH. When you fertilize, you're acidifying your soil. It's a salt, so you got to think about some of those things as well. Next slide, please. I really like this figure because it shows how soil pH affects availability of plant nutrients. The wider these bars on this figure, the higher uptake or nutrient availability. So you can see that most nutrients are most available within that kind of 6 to 8 range, and it depends. And then one thing to think about when we're talking about phosphorus management, phosphorus can become bound or stuck to soil particles at lower pHs. It would be iron and aluminum at low pHs and then calcium at high pHs. So making sure that your pH is adequate so that phosphorus is available to plants is something to consider, so we're not over applying phosphorus to soil. Obviously that has implications for water quality when we're talking about soil erosion and runoff. And then another thing that we commonly hear is buffering capacity of a soil. So that's its ability to resist change in pH. So in general, clay soils have a higher buffering capacity than sandy soils, and increasing organic matter in soil can increase its buffering capacity. So again, less susceptibility to changes with management. Next slide. Soil EC, or electrical conductivity, we don't deal with a lot in Wisconsin and other parts of the country. It's a much more common indicator of soil health. However, folks are really starting to use it as an indicator of soil health. It can be a measure of the amount of salts in soil. It directly influences crop yields, crop suitability, plant nutrient availability, activity of soil organisms, emissions of soil greenhouse gases. It affects soil water balances. So on that picture to the right, you can kind of see as you have a higher soil pH, it affects crop yield. I believe those are tomato plants. So it's something to consider. I think it's more an indirect measure of other soil properties. It's really easy to measure in the field. So folks are using it to sort of map field scale changes in yield and organic matter, productivity, things like that. So it's a really cheap and quick way to sort of measure other soil properties that are much more complicated to measure or get results on. So I think there's quite a bit of work in this area that might roll out as sort of a field soil health indicator. Next slide. All right, soil water dynamics. So we're going to cover a few different topics here. And again, these can get pretty complicated, so I want to try and keep it simple. But we're going to start with water infiltration. You'll often hear infiltration, permeability, hydraulic conductivity. Some of these terms used interchangeably, but essentially the infiltration rate is the speed at which water can be taken into soil during a rainfall event or an irrigation event. It's often measured in inches per hour. But basically it's a flux which depends on some of those inherent factors and hydraulic conductivity of soil, but it also varies based on wetness of the soil, the land use, land cover, slope, crust formation, etc. And then on that figure to the left, you can see you have infiltration rate on the left, and then hours since irrigation on the bottom, and each soil type or based on the soil classification can have a different infiltration rate. So sand, becomes or has a higher infiltration rate, obviously, than a clay might. And infiltration rates change over the growing season. They can vary across a field, even if the soil appears uniform. They can vary based on soil surface conditions. So if it's wet or dry, smooth, cracked, if it's compacted. And then if you look at that figure on the right, if infiltration rate is plotted over time, the curve eventually flattens. So you see where it becomes stable. That is your 100% saturation point, and then that is your KSAT, or your saturated hydraulic conductivity. So KSAT is used as a metric to quantify expected performance of soil during a storm event. So that's typically what we're measuring if we're in the field. I'll show you an image of how you can actually measure that. And then we'll touch on available water capacity, which is the amount of water that a soil or given texture will hold, and that's available to plants. Next slide. Next slide, please.
It should be on the next one.
Got it.
It's on my screen. All right.
Okay. All right, so continuing with some soil water dynamics, the big take home here is these other properties that we talked about, like soil structure, soil texture, mineralogy, all influence how water moves through the soil and how soil gives up water for plant uptake. So you can see on this bottom picture, you have difference in structures, prismatic versus platy, and how that water is moving through the profile. Obviously that determines erosion and runoff and plant uptake. And then you can see on that top table, different permeability classes and how those change with different texture classes. So you may use this in conservation planning. On the pictures to the right is a picture, I believe it's Jennifer using an amusometer. So if anyone's been privileged enough to use one of these, it's one way to measure KSAT in the field. It's very time consuming, but again, that's a good indicator of how your soil is going to respond to rainfall events. And then on that bottom right are infiltration rings. So a super quick way to demonstrate to a producer how compaction or changes in soil will influence the infiltration or the ability of, a 4-inch rainfall event to take up those 4 inches of rain versus running off the top. And last slide, please. I want to talk a little bit about the difference in water content between field capacity and permanent wilting point. So if you look on this figure to the left, it's demonstrating something called matrix potential. So under different pressures, usually, it's calculated under, you'll hear 15 or negative 15 bar, a third bar, etc. But it's basically discussing permanent wilting point, which you see is that negative 1.5 bar. And then between permanent wilting point and field capacity is your plant available water. So that available water content I mentioned. So that's a difference between pressures of negative 1.5 and that third bar potential. And then if you see between that third bar and 0, that's basically saturation. So water is moving through the soil via gravity, not matrix potential at that point. And the biggest take home here, I think, is that plant available water differs among soil types. So if you look at that figure to the right, if we're talking about plant available water, a sandy soil can hold much less water than a clay soil. So recognizing that differences in soil properties influence retention and availability of water, and then that can be influenced by organic matter, soil texture, bulk density, soil structure, etc. So if we're talking about resiliency to extreme weather events, whether it be drought or extreme rain events, understanding how your soil texture is going to respond to that and then using management to manipulate that is really important and another tool in our toolbox from a planning perspective. And that is all I have on soil properties. This is, again, kind of the building block for soil interpretation. So, we can come back to these. I'm sure there'll be some repetition, but there are some complicated properties. So I hope I didn't overwhelm all of you, and I'll send it over to Andy.
All right, thanks, Kristin. Great job. And yeah, don't worry if you are overwhelmed. We're teaching a one-day course on basic soils, and this is probably enough information to have a whole semester class. So what I'm going to talk about is some soil interpretation. So I'm going to kind of take off where Jennifer and Kristin left off, where they were talking about properties, and talk about how these properties are used to develop things called interpretations, which are the products we use to make a lot of conservation decisions. So this figure over here on this slide shows you some soil properties. There's this block diagram showing where soils occur in the landscape. And we use that information to develop a conceptual model of what's good, what's bad, what's limited, what's not limited for different land use decisions. This example I have is an interpretation I've been kind of working on, looking at suitability for black walnut tree habitat. And you can see some of the relationships with landscape position or soils types just in that snapshot of the driftless area. Here we go. Okay, so some of you guys might not even know what soil survey is, so I had to just throw this slide in there. So this soil survey is the product. It's a map and a series of information that contains a lot of soil properties and interpretations. It's all publicly available. This screenshot I have right here is from an app called Soil Web, developed by the NRCS and UC Davis. And for a long time, we've had maps of the soils of Wisconsin, but we still have soil survey offices scattered around the state that are continuously working on updating these products. So if you ever have questions about the soil survey, how to use it, that map right there shows you where your local soil survey office is, and they're probably the best equipped to answer any questions you have, but also feel free to contact me anytime. So what's really cool is I can look into our database and see what most people using web soil survey are clicking on. What are the most popular interpretations? What are the most popular properties that people look at? And this graph kind of shows you that list of the top 10 from last year. So if you look at right up at the top, the most commonly used interpretation from web soil survey is hydrologic soil groups. And there's a reason for that. They're used for grass waterway designs and culvert designs. Then another one, depth to water table. And so there's all these different interpretations. There's some that are suitabilities or limitations, like suitability for roads or susceptibility risk to corrosion of steel. There's also other interpretations that are numeric, like crop productivity indexes, soil erodibility factors. And then there's some that are just their own unique classes, like hydrologic soil groups, drainage class, farmland classification. But all of these interpretations use different soil properties, and they come up with some sort of product that we can look at in web soil survey. So I'm going to talk about some of these. I'll try to be really quick. I know we're a little bit behind on time, and I do want to have some time for questions, so I'm going to kind of fly through this. If you have any questions, you can always contact me. So the one I always start off with is dwellings with basements, because almost everybody can understand this. So we take properties like shrink swell potential, depth to hard bedrock, slope, texture. All of those properties are considered and used to develop a thematic map that shows us what's limited and what's not limited for housing with basements. So in the screenshot of an area in Dane County from Web Soil Survey, you can see areas that are good for developing houses with basements, areas that are bad, and areas in between. And over down at the bottom, you can look at this in a tabular format. We're going to talk about map units and components later on. But for each map unit, you can look at the rating for each soil in that map unit, and then also look in a column and see why it was rated as such. And you can see this first soil that we're looking at is very limited because of shrink swell potential and because of depth to hard bedrock. Typically, the higher the number in that rating reason, the more influential it was on making that determination of the rating. So there's a really simple, we start off with a really simple one. This one's a bit more complicated, talking about drainage class. It's really varies state to state how they define what's well drained versus what's very poorly drained. And it's really not just an indication of where the water table is. It also considers how long is the water table there and how fast is water infiltrating through that soil. So looking at this figure, this was developed in Rhode Island where I grew up, and it shows you drainage class along a Katina sequence of a hill slope. You can see over on the left you have well drained, over on the right you have very poorly drained, and it should be self-explanatory. Very poorly drained is going to be really wet, well drained is going to drain very quickly. And we even have another class called excessively well drained. That would be pretty much like a pile of sand, which I have a picture of in the bottom left. And the way we identify these different drainage classes is we use something called redoxamorphic features. So if you look at that picture that's second to the left, you'll see a lot of discoloration, some orange, some grays. Those are iron transformations that occur in the soil due to saturation. So the most basic way to explain this is as soils become saturated, iron gets mobilized, it moves around, and then you're left with that naked parent material color, which is the gray colors. And then as the soil dries out, it oxidizes like a rusty nail, and you have the orange blotches. It's a bit more complicated than that. It actually includes microbes in the process, but it's a very good indicator of where the seasonal high water table is using those features. So you guys that are engineering technicians, anybody just trying to dig a hole and figure out where is this wet or not, looking for those iron features is a really good indication of your drainage class. Other features we look at are things like the thickness of the epipedon or the surface layer. If you see really dark surface layers like that one over on the way right, that's usually indicating that the decomposition of organic matter is slowed down due to saturation. Microbes like oxygen, if there's not a lot of oxygen, they can't really keep up with decomposing all of that organic matter. So these pictures just show you a sequence from left to right of a really dry soil over on the left that I took from a really sandy soil in the California Central Valley to a very poorly drained soil over on the right, where you can see that gray depleted zone in the subsoil because all of the iron is pretty much leached out of the system. So this is what drainage class will look like when you go into Web Soil Survey. You can see the legend over on the right. And these next couple slides are just examples of how you could use that information for conservation planning. So there's this really cool tool for coming up with cover crop mixes. I'm sorry, I told you guys I wouldn't go down the soil health route, but I can't help myself. So we'll just talk about this really quickly. So there's this really cool tool. I'll send you guys the link, but you can input your state, your county, your goals for using that cover crop, and then specify your drainage class. And that will help you come up with a list of species that might be good to plant on the field you're considering, and then when to plant them as well, and their rating for those goals that you would like to fulfill. Then there's things we consider hydric soils. These are our poorly drained and our very poorly drained soils. A lot of you guys probably use this map over on the left or something like it if you're doing wetland compliance, but I just wanted to really talk about this really briefly, that a hydric soil is a soil that forms under reducing conditions. We don't like farming hydric soils or destroying our wetlands, so we try to protect them. So that might be one of the soil survey products that you use, or one of the interpretations. And over on the right, that map shows you kind of what it would look like in Web Soil Survey when you look at it. Up in the top right, that is a really good, useful guide for identifying hydric soils. So there's different indicators depending on what soil you're looking at. Land capability classes. I had to talk about this. I'm not a huge fan of land capability classes. They're very general. I don't see them as being very useful for anything, but since land capability was in the title of this course, I just had to show you guys. So if you look at this, it shows you what the map would look like in Web Soil Survey, the different classes, but that figure on the right really hits home. It really shows you what these classes mean. So classes 1 through 3 are pretty much land you could farm. Maybe 2 and 3 will take more preparation or input to farm, but yeah, so they're all farmable. And then once you get into higher numbers, you can see their land use potential kind of decreases, and something that's class 8 you might just want to leave as natural vegetation. So the way I would use this would maybe just to get a general idea of a property that you're looking at and its potential, but it's not going to help you come up with a specific cover crop mix or anything like that. It's more of just a general idea of the inherent properties of the soil and their potential. This is another one that's really commonly used, is the farmland classification. So this is developed a little bit differently. It's not just looking at the specific soil properties and running it through a calculation that determines is it prime or is it not prime. This was determined at an earlier date by probably a state soil scientist who came up with a list of soils that are either prime farmland or not prime farmland. The reason I just wanted to show you this is because it might come up in your job. You might get a request about something called FPPA. It's the Farmland Protection Policy Act that was mandated, I think, it pretty much says that if we're going to use federal funds to manipulate or destroy prime farmland, we'd better have a good reason, and we have to review those requests. So if you're a DC or a SoilCon, you might get an FPPA request. The procedure for that is just give it to your area resource soil scientist, and they'll take care of it, or send it to me and I'll give it to one of them. So next, we're going to talk about some of those numerical interpretations. One that you'll probably use a lot is this National Commodity Crop Productivity Index. I'm going to talk about some of our other productivity products, but this is a nationally developed one, so it's consistent across the whole country. You can see it identifies soils of ranging from high to low inherent productivity. And then if you pull up the tabular data, which I did over on the right, you can see there's a numerical rating. So the higher number, the higher the productivity of the soil. This can be a really useful thing if you're doing some planning and looking at a property and trying to identify what are my high productivity areas versus what are my low ones. So I really like this interpretation. I think it has a lot of uses, but we also have a state-specific productivity index, and then there's also some yield information in soil survey. The thing about the Wisconsin productivity index that I like is that it's developed for our state, and when Jason Niemanchek, our previous state soil scientist, developed it, he was really just thinking about Wisconsin soils. The problem with it is it wasn't really well vetted, and there's some issues with it. I've seen just some weird errors where it really doesn't align with the national productivity index. So what I just tell people is know that this exists, use it if you like it, but be wary of it, compare it to the national one, think about it rationally, and if the number makes sense, don't just use it blindly. But I just wanted you guys to know that existed. And then this productivity yield information, I would say do not use it or use it with a lot of consideration. You guys probably know what's reasonable bushels per acre for a soil that you work with. I think when I look at these, they seem pretty low. And it's probably because when a lot of these yield estimates were determined, it was a long time ago when we didn't have the varieties and the farming practices and the fertilizers that we have today. So I'm sure for a lot of these soils, you could probably double their bushels per acre. But if you just look at it relatively soil to soil, then it might be useful for you. This is the one that was at the top of the list, hydrologic soil groups. I've probably talked about hydrologic soil groups more than anything since I've been here in Wisconsin. They're very important, but it's also one of the most misused soil interpretations. So hydrologic soil groups are groups of soils that have similar runoff potential under similar storm and cover conditions. So when we develop hydrologic soil groups, we're developing for a soil, assuming that the soil surface is bare. We're not considering the crop or whatever land use is on top of that soil. And like I said, it's groups of soils with similar runoff potential. A lot of times people are using this and trying to group soils with similar infiltration rates. And that does work. A soil with low runoff potential is going to have higher infiltration rates than a soil with high runoff potential, but that's not what this tool was developed for. So the exact breaks between an A and a B and a B and a C might not be that meaningful if you're thinking about infiltration or pesticide leaching or whatnot. So don't misuse hydrologic soil groups. Use them for what they were designed for culvert design, for grass waterway design. So there's 4 groups. There's also these dual classification groups, which I'll talk about a little bit more. And the way these groups are determined is looking at that saturated hydraulic conductivity that Kristin talked about, the depth to the water table, and the depth to the restrictive layer. So a lot of times when I see people using hydrologic soil group data inappropriately, I just point them to these properties and I say, just pay attention to these properties and not the specific groups that seem kind of arbitrary to me. So I did mention these assumptions. I won't list them off. I'll just keep going. So this is probably a little bit overwhelming, but you'll have this slide. You can always go back to it, but this just shows you how those criteria are used to indicate the 4 different hydrologic soil groups. You can see there's more variety in Class D soils. It could be anything such as a soil with bedrock within 50 centimeters or a well-drained soil with just really low KSAT rate. So just be aware that there's different criteria. All hydrologic soil group A soils aren't equal. And I just have an example over here on the right. And then there's these dual classes, and these can be a really big pain because what they mean is that the soil is a C hydrologic soil group or a D hydrologic soil group unless it's drained. So if it's drained, then you can consider it a C. So if you're designing a grass waterway and you come across one of these dual hydrologic soil groups, you're going to have to decide, is this a C or a D? Is it drained or not drained? And so this might take some on-site investigation. This map over on the right was actually a design in Barron County that I went out with one of our engineers. you could see is a really large soil map unit. It's a big giant polygon, and it's all mapped as a C/D. So we went out there and we took some samples. We realized that the mapping was really coarse. We could map it at a little more precise scale, and then we could determine what was drained and what was not drained out in the field. And then what happened was we came up with a more legitimate grass waterway design that wouldn't cost so much as one if you just designed it all assuming it was a D. Then there's these soil erosion factors, and I can't go too far deep into these because we're running out of time, but a lot of you should be familiar with them already. There's the K factor, which is the soil susceptibility to sheet and rill erosion. It's a factor ranging from 0.02 to 0.69. We have a really good set of posters, or I say really good, you might not like them, but there's some posters online that I'll also post a link to in the chat that kind of explain what K factor is and what T factor is. This is the one over on the right for T factor. So it shows you the criteria, it gives you some examples. What T factor is the maximum tons per acre of soil that could get lost without affecting crop production. And then we also have a wind erodibility group and an index, and that's showing the soil susceptibility to wind and cultivated areas. So we've gone through a lot. I could only mention so many interpretations. Kristin could only mention so many properties, but I just wanted to point this out now, and I will reiterate this later, that when you're in Web Soil Survey and you can't find one of these things, really utilize the search bar. It's really helpful. There's just interpretations buried within folders, properties buried within folders, and sometimes even I, who have used Web Soil Survey for 10 years, have a really hard time finding things. So utilize that search bar, and also always feel free to ask your local soil scientist for technical assistance. I love showing people Web Soil Survey and helping them out, and I'm sure a lot of other soil scientists in the state feel the same way. So thank you. We only went a little bit over time, but we have some time for questions. Let's see, our next module starts at 11. So you got 3 minutes if you have a question. I see one, how often are the yield information updated? Never. We do not update that information unless I'm unaware that Wisconsin is doing something weird here, but we do not look at that because yields are really more impacted by the farming practices that are there and not so much the inherent properties. So we've kind of drifted away from populating yield information, and we've relied on that more of that productivity index. So be wary about the yield information in Web Soil Survey because it's probably that historically collected data. Somebody's asking about the field book for sampling and describing soils. I will put the link for ordering the hard copy, or I think Jennifer might have already posted some ordering information.
Yeah, Andy, I looked and I've been scrolling through and I did the process they said, and I still, so if you come up with something, please share it in the link, please, or in the chat. Okay,
I will put that on my list to do. We got a question for Kristin. We got a couple minutes before the next module, so let me read this one off. Isn't the soil pH also impacted by parent materials as well? So she provided an example comparing limestone and sandstone bedrocks, and yes, the pHs from those soils of those parent materials would be much different. But Kristin, do you want to attack that one?
Andy, I think Kathy and I kind of addressed it.
Oh, okay.
Yeah, I was trying to unmute myself. Yes, definitely parent material mineralogy influences those factors, just like CEC. But I think, you know, from our perspective, understanding how management influences it, fertilization, irrigation regimes, things like that, in those surface horizons has a much greater impact than, you know, the inherent pH of the soil.
Okay, great. Well, I'm going to give everybody a minute or two to go to the bathroom, and then we'll start the next module up pretty soon. Do we have Jeremy here?
I'm here.
Okay, so Jeremy, let's just start at like 11:05 just to give people a second. I think your module is not going to take a whole hour, right?
It shouldn't.
All right,
If
cool.
it does, we're all in trouble.
All right, let's just give people 5 to run to the bathroom. I'm gonna go myself, so I'll be right back.